Okay. Okay, please continue. Hello? I was talking to you. I was just saying that apparently we are alone. Then there is nobody remotely. Then we can hide the solutions of the homework, right? Only us can know that. Okay, then we are getting towards the end, right? Which is making me happy and you're not that much happy, right? Okay, now today we'll talk a bit about the solutions of homework 3. I'm not sure if I published them already, most likely not. I will do that, and I will also give you the last homework and quite soon the final one, where you will have to fight the beast, right? Okay, now this was about multiplication, and the first question was how to do binary sign digit multiplication. And we had an example, then how to do that using right shift, and then when we deal with normal binary stuff, you know, the generation of the partial products is just an AND gate. In here, because we deal with sign digits, things are getting a bit more complicated, and the second question was about how to do the generation of the products. Now, this is not such a big deal. Then essentially what we do exactly what we knew, but now instead of adding A, we may add A, 0, or minus A, depending on the value of the digit. Let's say now it's minus 1, because it's minus 1. I have to multiply A with minus 1, which will give me minus 1, 0, 1, 0, minus 1. And then I'm continuing the work exactly as things would have been in normal binary format. This is not such a difficult question. You could also try to do it the other way around, starting with the most significant digit. Things will be similar. Now, the question is, how do I generate the partial products? And you see, when I do that by visual inspection, things are fine, but I have to do it by hardware. And I have two possibilities. I can think about a circuit which will take one digit and A and generate the result, or I can do things at the digit level. Then I have two digits, two sign digits, and I'm multiplying them. And then what I want to do, and this is the solution that I have, I want to do a binary sign digit multiplier, which means I have two digits and I am multiplying them. Now, the solution will very much depend on the encoding that I'm using for the sign digit. As I mentioned, every now and then I do not appreciate when you eat or you drink during the class. Then, in my case, I made the choice for that encoding. But you could have chosen a different one. What would not have been that? Then, first step is to make the choice of the encoding. If you don't do that, you cannot go further. Second step is to do some kind of magic, and based on this encoding, to derive the equations for the product. Now, if I assume that Z is the product of those digits, what I have to do is I will have to make a K-map. Do you remember Carnot maps? Then I will make a K-map, and on that K-map I will have to consider 4 inputs, because I have 2 digits, but each digit is represented by 2 bits. And you remember them, right? Okay, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, and I put here X and Y, and then I have to make two such maps and fill in the value of XS and YS, and then do the minimization. Now, for my encoding, this is the result. Then the sign is actually the XOR of the signs, which is kind of intuitive, and the magnitude is the product of the value is the product of the values. I can also make some kind of logical explanations behind that, or I can rely on k-maps. I fill those with zeros and one, and then I do the minimization. It sounds familiar, I hope. You are very quiet. I think you are fascinated by the beauty of this k-map, which has no closure here, right? There is some kind of leaking. Okay, now, in order to refresh your skills and, let's say, capability to work with k-maps, I will advise you to try with another encoding. And let's say to encode negative, positive, and see what you get. Then this exercise is not difficult, basically. But this is a small logic design effort. You may have to do a minimization of a function during the exam, then I will advise you to try to do this, right? Is this clear? Do you have some troubles with doing k-map stuff? I hope you don't, because otherwise I have to do it myself, which is tiring. So far so good? Okay, no answer means yes. Now, next question was related to the recoding. And then now, in the book, we have radix 2, we have radix 4 encoding, and in here we have radix 8. And in radix 8, the principle is the same. Then this is booth recoding. What you want to do is you try to diminish the number of values, then to get less ones, and then to do a kind of speed up of your calculation. Now, because it is radix 8, you will have to inspect 3 bits. Radix 8 means that I'm considering 3 bits at a time, but I always have a reference. Then when I was doing radix 2 of radix 4, I was considering 2 bits at a time and 1 reference. In here I have 3 bits at a time and a reference. And then practically what you get is something like that. Okay. And then those are the 3 bits which you are inspecting. It's radix 8, then values are between 0 and 7. This is your reference. And now you can apply the same principle as the extension from radix 2 to radix 4. Then you encode this based on these 2. You encode this based on these 2. You encode this based on these 2. And then you arrive to a digit, which is now in your digit set, which is -4 to 4. Now, I did not type here the explanations, but they should be kind of straightforward from the tables in the book. Okay? I'm not giving you everything. I'm just trying to push you. Yes?
On row 7, couldn't you...
row 7, I don't know which is row 7.
0, 1, 1, 0.
0, 1, 1, 0, yes, in here.
Couldn't the encoding also be 1, 0, -1?
1, no. 1, 0, -1. Sure. Sure, it could. You can do that. Also, it's also true for some other rows that things can be different. But at the end of the day, what is important is this one. Then Basically, what is this exercise telling you is that I can construct encoding for any type of radix, starting with whatever I have in the book, which is radix 2. From radix 2, I can go to radix 4, to radix 8, to radix 16, and whenever I'm doing that, there are two phenomena. First of all, I will consider more bits at a time. Always I need a reference in order to know what was before. Remember, what I'm looking for are strings of 1. And I need to know if a string of 1 just finished or what happened before it's helping me. That's one point. Then the second point is that taking pairwise, I can determine some kind of intermediate values. But I can also think in a different way and consider this like a number which is represented in 2's complement. And if I do that, this is the most significant bit, this is the least significant bit in this 3-bit scanning. But there is an overlap. And this overlap is just this bit, which has the same weight as this. Then if I consider these 4 bits according to this representation, I will get this equation, which is actually the solution of the second question. You can easily check that in the table you will find that by applying this, you will always get the right results. Now, you have to remember what the purpose of boost recoding is, right? Then, the purpose of boost recoding is to consider more bits at a time, then you do high radix. That's one. Then, without or with boost recoding, high radix will give you less partial products, but wider partial products. And second is you are trying to diminish the number of situations where you do calculation. Now, from here further, things can be done in different ways. What you have to do is you have to find an implementation of the previous table. And the previous table is telling you the following story. You consider 3 bits from here and the reference. Then based on those 4 bits, you have to generate signals for this max. And the signals for this max will select 0, A, 2A, 3A, and 4A. Now, you see it's a 4-to-1 max. I just mentioned 5 possibilities. The 5th possibility is actually given by this enable. Then if the max is disabled, I'll have 0 in the output. If the max is enabled, I will choose one of those. That's one part. And the second part is the control for addition or subtraction. If I have a negative, I will have to complement this guy. Then here I'm taking care of the magnitude. With this control, I am taking care of the sign of the product. Is negative or positive? If it is negative, this will select, an XOR to do complementation and will be a hot carry input into the final header. Now, this is the logic which is generating the non-zero. This logic is not finished, and you can try to do it. Again, you use a K-map.
Problemen?
Er is niemand, blijkbaar.
Oh, er is iemand aan de andere kant?
Ja.
Oké, dan moeten we even bellen met Eindhoven of Twente. Ja? Oké.
Ik heb begonnen.
Ja, nee, begin maar, ja.
To switch back. Dutch is disturbing. No, I'm not kidding. Because Dutch is very close to English. If you speak quite frequent Dutch, you lose your English. As foreigner, I don't know when you are native, probably is different. Okay, now this design is done. This is telling you something about the complementation, and this is obvious from the table. Whenever you have negative, right? It's when this is 1. This is a special case, but 0 and minus 0 doesn't matter. Okay, now in here, in order to complete this logic, you have to understand how the selection is done. You see, the selection in here is not exactly intuitive. I could have connected in different ways the inputs. But this number in here is telling me what combination I should get here in order to select this input. Then if I have 0, 0, I will select 4A. If I have 0, 1, I'll select A. 1, 0, I'll select 2A. 1, 1, I'll select 3A. Most of the time what you do, you see A, 2A, 3A, 4A. But doesn't matter the order, as long as the control here is providing the right signal. Okay? Another thing is about the generation of A, 2A, 4A, and 3A. Now, A is just what I have. 4A is A padding with 2 zeros at the end because it's like I'm shifting it to position. A is padded in the most significant part with 2 zeros. 2A is 1, 0, 1, 0, and 3A I'm pre-computing. If I don't want to pre-compute, I will make this structure a bit more complicated. Then I will need some kind of reduction tree, maybe some carry save adders to generate 3A. But I decided to pre-compute. Now, any solution is good as long as it's coherent. And there is no kind of requirement to bring, an optimized solution. Then whenever in the statement of the design issue, there are no constraints on different things, you should not bother.
Hello?
Hello.
Just received a call that they cannot hear you.
But I cannot see them.
Okay.
They could hear me if I would start doing this, but
Okay.
I didn't know they are there.
Yeah, they are here.
Okay.
Let's see.
I was assuming that we are home alone today.
No, they are here.
Okay. Okay. But, hello, can you hear me? I cannot see
No,
you.
I know.
You are talking, right? Yeah, hold up. This is called interrupt, right? Oh, it's a brilliant interrupt.
Was laptop 1 or 2?
1, I guess. What should I do when I get an interrupt?
Immediately service.
Okay, then I will continue. I don't know if they can hear me or not. I cannot see you, I cannot hear you, but I can assume you are there. Then practically when you have a problem, you should optimize
Yes,
only. Okay,
Yes?
hi guys. Okay. I cannot hear you, but I hope you can hear me now. I didn't know you were there.
Okay.
Then okay, then you had the question.
Is this assuming unsigned numbers, since we're padding with zeros in the most significant?
These are unsigned numbers, because the sign is coming later on. This is always positive.
No, the reason I asked is because on Farhami's website,
Yes.
He mentioned that that it should be a minus. It should be padded with 1.
Okay. If A is signed number, then you have to pad it. You do sign extension. It's true. But in here, I think it was in this, or maybe not. Was it said if it's signed or unsigned?
He said it that it was an errata. It should have been padded with 1.
Okay. But that's then your comment. It's okay. But in this solution, we assume that A is unsigned number. If it is signed, you just have to sign extend. Okay. Now, in order to design this logic, as I said, I have to make the assumption about what I'm selecting, and then look in the table and implement two functions, which are now 3 input K-maps. I just write all the combinations, and then I write 0, 1 here. I do the minimization, and I'm in business. By the way, when I say design something, there is always an extra explanation. If there is no extra explanation, it means that I want to see the equations. If there is an explanation further, I may say I want to see the structure of the circuit. Then when you do things with full adder, half adders, you know, it is easier to put the dots and then to draw the boxes and then to let me see how the bits are generated and stuff like this. When I refer to that kind of logic design, I don't want you to be, I don't know, Rembrandt. You know, we are in the Netherlands. I was thinking about Da Vinci, but then I don't want you to make a beautiful drawing. What I want is I want to see the equations, and also I want to see how you arrive to the equations. Because just writing down the solution is not enough. It may, you know, there is radiation going on, and you might be exposed to some kind of non-permitted radiation in the class, and then just write down an equation which does not belong to you, which could be also wrong, by the way. Then. Okay. Now, in here, this is the encoded that we assumed. As I told you, this is not quite intuitive, but doesn't matter. As long as the selection is right and you follow the table in your implementation, things are okay. Okay, did you arrive to something in this direction? As I said, this question has more than one solution, actually a lot more. If you don't make simplifications, you can make your life very difficult. Because there are 4 inputs, and then the table can get very complicated, and this logic may get kind of ugly. And this is the reason why we relied on this. But you can also design here in a different way. But at the end of the day, what you need in order to solve this, it's a table, which is correct. Now, if the table is not correct, but the implementation is correct, you get points for that. But you don't get points for the table, right? Then you get points for whatever you are doing good. Then the data dependencies are cut. Then I evaluate you in pieces. Then I split usually the assignment in parts, and I give you points for each part, and I'm trying to decouple them. Okay, now, next one. Okay, next one is about the realization of a 6-to-2 counter. And then what I want to do is I want to design a 6-to-2 counter. Now, remember the philosophy of those counters. Then I am getting a lot of inputs, but I'm only generating 2 outputs. On 2 outputs, which are current position and next position, I can represent values between 0 and 3. In order to conserve the value and do the calculations in a proper way, I have to generate some carries to my neighbor, to the neighbor, after my neighbor, and on a kind of distance from the current position. The idea, however, is to generate the carries in such a way that I'm not creating dependency between the positions. Then carries from position I are getting into position I plus 1 later in the calculation, but not at the end of the calculation, such that they can be considered in the calculation. That's the philosophy of those counters. Now, in order to have a good design, I have to determine the number of carries. Then, my current number of inputs plus all the carries that I'm getting, because I'm giving carries, but I get carries too, should be smaller or equal to 3 plus 2 times carry from my neighbor, 4 times carry to the next one, and 8 next one. And now I have to find some solutions for that. And because n is 6, this is a solution. Then if I consider phi1 3, I have 3 times 2, 6, plus 3, 9, 6 plus 3, 9. Then I'm in business. I am doing the right calculation. Then I'm getting 3 carries, 3 units. I get 6, which are my inputs, and I'm generating 3 values, which are in my position, and I am generating 3 carries to the next position, which will count for 6 as unit. Now, having said that, this is the design. I consider the 6 inputs, and I apply full adders. Now, I cannot report all of them. I have to give carries to my neighbors. Then I will select the sums to stay and the carries to go to the next position. Now, in the next level, what I'm getting is this sum and 2 carries from the previous position, which are those carries, but now of the counter, which is here. Now, after this compression, I have something for local and a carry for the next one. Then I have 1, 2, 3 units. This one is coming now to me from my previous guy, and I have this, plus this, plus this, will give me this value, which is my sum and my carry, and those are the 2 outputs. Then my design has 3 levels, and I am getting carry from the neighbor in such a way that I can use them in the right moment. I can use them in time. Then if those carries will come, let's say, at this moment, they would create a problem for me. But because they are coming at this level from this, then I hide the delay. Now, this is one solution. There is another solution, and the other solution is this one. I can assume that now this is 0, and I'm only generating carries to the next position. Then not to my next, next to next. Then, if those are my counters, okay, then I'm generating here 2 outputs for me, and I'm generating something which is going from here to this guy. And this is I plus 1, and this is I plus 2. Now this, it's also legitimate. It's fulfilling my equation. Now the question is how this design will look if I'm changing that. Did you arrive to something in that direction, your solutions, or you didn't try this question? I will rephrase. Who tried to solve the question? Okay, and who succeeded? You guys? You are very quiet. Then try now to solve the question with the second solution. Then instead of generating carry to the next, I'm generating a carry to the second next, which means my intuition will tell me that the designs are kind of similar. And I would say that practically this full header will get these two inputs and nothing coming from here, and the rest will be the same. That's my guess for the design, but I would advise you to try it. There is a, yes?
Is there a reason why on the bottom of this slide there is a carry propagated from the previous position?
Yes, because 1, 2, 3, 4, 5, 6. I'm applying this and I'm generating one here and one here, right? The column in here, which is also taking 6, is generating one here and one here. And this is that one. Then I'm assuming I am in a context. That this is not a real input, but because I see those carries coming and this coming, this is also coming. It's not taken into calculation, but it will be coming in my position as contribution. You are very, how should I put it? Are you depressed? 5, it's spring. Yeah, spring depression. Yeah, what can I do? There are some solutions against depression. You know, one is to drink, not water, alcohol. It's not really helping. It helps for a while, it's like a temporary solution, but it's not helping. The other one is to do some physical exercise. They said it's good. And I think the final solution, which is the best solution, is to study for computer arithmetic. Oh. That will certainly remove your depression. Why are you laughing? It's such a beautiful topic.
Yeah, but it doesn't help with depression.
It will. When you see the beauty of a mathematical solution,
I can see the beauty in physical contact.
you know, there is, when you study engineering, you get a master in science.
And
When you study mathematics, you get a master in arts. No, I'm not kidding. And in Dutch, how is mathematics? Wiskunde, the art of counting. You can translate better than me. And it's kunde, right? It's art. Okay, this is, okay, it's a combination of art and engineering. Okay, let's look to the next one. Then the next one is, I want to design a piece of hardware which is doing the calculation of the P, which is A times X plus Y plus Z, where A and X are K bit, and the other ones are L bit, and all of them are unsigned. If I change that to signed, things will change. And might be a good idea to try to do it at home for signed. Now, the first question is to determine how many bits do I need to represent P? And the second one is to design this hardware by using Wallace and Dada, and then to show that an 8x4 array multiplier can be utilized to compute that. Now let us take it one at a time. This is mathematics, and this should be simple. What I'm doing is I'm making the product of two numbers and I'm adding two other numbers. If I want to determine the dynamic range, because this is unsigned, is between 0 and a maximum value, which is to a k minus 1, to a l minus 1, to k minus 1, to l minus 1, because depending on how many bits, this is my maximum value. If I would do things in signed numbers, then I will have maximum and minimum values. But the number of bits will stay the same. Now I do here some kind of multiplications, and at the end of the day, the maximum value is 2 to the power k plus L minus 1, which means that k plus L bits are enough. That should be clear for everybody. If it is not, we should revisit it. No, brilliant. Now that kind of evaluation, now you knew how many bits are required, but in practical cases you may want to know. And then this kind of evaluation can be very useful. Now second part was to do a design. Now this is not looking like a design, this is more like a piece of art, but this is what we understand in here by design. I draw the partial product structure, then the first 4 rows are a times x, then I have z and I have y. You see, some operands are 4 bits, other operands are 8 bits, and now, because this is Wallace, whatever I see, like 3 dots, I'll cover them with full headers. And I have 1, 2, 3 steps of compression, and in here I have a carry propagate header. As you see, I could also have applied here a half header, then to generate a dot here, and then not to use the carry, but that would not have helped me, because anyway this would remain the same dimension. Now I save a half header here by utilizing the carrying of this carry propagated. Yes?
First I have a comment and then a question. By the first stage you said you had 9 polaris, but I count 10.
Maybe there are 10.
And the question is there more than one Wallace tree that you can derive? Like my implementation wouldn't have half adders in the first stage, but like for the data tree you have to follow the table, but for the Wallace, is it?
You can do whatever you want in order to get as fast as possible to the solution. Now, if by not applying the half headers here, you get the same depth of the tree, it's fine. But if you don't apply the half headers here, you will apply more full headers later on. Then the principle of Wallace is greedy. Then you try to push towards 2 lines as fast as possible. But there are choices. And sometime, you may decide not to compress those, and this will propagate here in more full headers. When we talk about data, then you have to be careful not to overcompress, okay? And that one will be penalized if you do that in the context of an assignment of the exam. In a context of the design, I don't know, this will depend on what you want to achieve. Okay, now this is the other solution. You see, I'm doing less work and I am obtaining a different cost. Now what you see, it's here in this design, it's very much clear that Dada managed to save me some hardware, but generated me a 12-bit carry propagator instead of a 9-bit, right? It was 9-bit. Which can be very bad. This can have an influence on the delay, on the performance, which can be substantial. Now the last part was about using an 8x4 array multiplier to do this kind of calculation. Now if you look at the array multiplier, you will see that there are inputs which are not utilized. There are inputs which we don't really use. Now because of those inputs, you can actually connect the additive values, which are y and z, to the array multiplier and being added. You just draw an array multiplier and then you see there are some inputs in the array multiplier which you not use. And there you can attach X, Y, and Z. Quite sure the array multiplier will be slower, a lot slower than this design. But what the purpose of that question is to demonstrate that in an array multiplier, you have an extra level of freedom. Because some of the inputs are not utilized, you can add their additive inputs at no cost. Okay, the final one. What is the final one? Design of squares.
Also 12.5.
Sure.
12.5 you also did this.
Ah, oh. I wanted to finish. But you are awake, which is better, right? Then I have some 2.4 add multiply models, and I want to use them in order to construct in a hierarchical way 4 times 4 add multiply modules. Then how do I do that? This is a simple question, I would say, and I can solve it in 2 ways. Because my basic building block is 2 times 4, and my building block is 4 times 4, my intuition will tell me that 2 of those will be enough. I just have to know how to connect the inputs in a proper way. And I can do that by kind of, thinking on the equations, or I can do that by looking on the diagram of the 2 designs. Then this is the dot diagram for the 2 times 4, and this is the dot diagram of the 4 times 4. And I can try to cover, parts of this diagram with 2 times 4, and this is 1, which is generating this, and now this is the second. Then 2 of them will be enough. I can also think about the fact that I can consider parts of my operands. Z is twice as large in this case. Then I will consider half of it in the first level and half of it in the second level. And also A is twice as large. Then I will take 2 of rows of the product A times X in the first level and 2 in the second. Then I can draw this diagram in 2 ways. Then exactly how you have the diagrams in the book with designing things with add multiply models, in the slides. You have a design in the slides, and there is one based on dot diagram and one on how you partition the operands. Then I can rewrite the calculation of this by considering partitioning A and Z in 2, and then I do first the calculation for the least significant part of A and Z, and then for the second most significant part, or I can just try my luck looking on the diagrams with covering the dots. Now I have to be careful when I'm doing that, because if I'm not understanding what I'm doing, I may try to overdo it, which will create me troubles later on, because I may have to use more units in order to fix it. And in here, my assignment was to use as few as possible. Now, the second part was about the squarer, then to design a 4 times 4 squarer. Practically, because those are the same, you have here X, here you have twice this product, which will go here, here. You have twice this product, which will go here, and then by making that kind of thing, this is what you have. Then all of them are nice, except for this guy. And in here you apply a full adder, which will give you sum and carry, and then you apply a carry propagated of 5 bits. Now, in the final part, you were said to utilize this kind of, that was the key. Then you replace this with a carry into apply this trick. This is what you obtain. You start with the previous. Then from here is the same. Now this is 1 and this is 2. You rewrite them based on the previous equation. And this is what you have, which is now, 1 bit short. And then you are in business. And then you get a break. If you don't have questions, if you have questions, you don't get a break.